A single river of plasma stretches across the universe, hotter than a star, carving the shape of everything we see. And the most colossal of these hidden superheated streams is something almost nobody can imagine. Stay till the end to discover number 1. Imagine the heart of a Seyfert galaxy spewing out a wind of ionized plasma that blazes at millions of degrees, carving narrow tunnels through its host galaxy. These outflows, driven by a supermassive black hole's voracious appetite, can extend tens of thousands of light years, heating surrounding gas and triggering shockwaves that ripple across the interstellar medium. Researchers estimate the mass loss rates rival those of entire dwarf galaxies, making these streams key players in regulating star formation. While they appear modest compared to cluster-scale filaments, their influence on local galactic ecosystems is profound, and they set the stage for the larger, more dramatic structures we'll see next.
Surprisingly, the remnants of ancient galaxy cluster collisions light up the sky as elongated radio relics, tracing arcs of superheated gas stretched over millions of light years. As two massive clusters merge, their intercluster mediums slam together at speeds exceeding 1,000 kilometers per second, compressing magnetic fields and accelerating electrons to near-light speeds. The resulting plasma glows in radio wavelengths, revealing filaments that can span half a megaparsec. Though invisible to the naked eye, these structures map the shock fronts that reheat the intergalactic medium, feeding the cosmic web's backbone. Their sheer scale hints at the power of gravity on grand scales, and they lead us toward even hotter, denser bridges that dominate the next tier of our list.
Over the past decade, astronomers have pieced together evidence for the elusive warm-hot intergalactic medium, a diffuse network of gas heated to 1010K that threads between galaxies. Detected via faint X-ray absorption lines against distant quasars, WHIM filaments are believed to contain up to half of the universe's ordinary matter. Though tenuous, just a few particles per cubic meter, their cumulative length stretches across hundreds of millions of light years, acting like invisible highways for heat and matter. Simulations suggest they form where gravity pulls gas into the cosmic web's scaffolding, then shock heats it during large-scale structure formation. Their hidden nature makes them challenging to image, yet they are a crucial reservoir that fuels galaxy growth. Up next, we'll explore shock fronts within merging clusters that heat the WHIM to even higher temperatures.
Hidden in the chaos of colliding galaxy clusters are shock fronts that roar through the intracluster plasma at supersonic speeds. When two massive clusters converge, their hot gases slam together, generating pressure waves that can travel thousands of kilometers per second. These fronts heat the surrounding medium to temperatures exceeding 100 million Kelvin, creating luminous X-ray edges observable by space telescopes. The resulting superheated streams act like cosmic furnaces, re-energizing particles and amplifying magnetic fields. Measurements indicate that the energy deposited by these shocks can rival the total output of all the stars within the clusters combined. Their dramatic influence reshapes the thermal landscape of the cosmic web, paving the way for the spectacular Quasar Jets we'll examine next.
Few people know that the most focused beams of plasma in the universe emerge from quasars, active galactic nuclei powered by supermassive black holes. These jets launch streams of ionized gas at relativistic speeds, sometimes extending beyond 1 million light-years into intergalactic space. Temperatures within the jets soar to billions of Kelvin, making them visible across the electromagnetic spectrum, from radio to gamma rays. The kinetic power of a single quasar jet can equal the combined luminosity of an entire galaxy, injecting vast amounts of heat and momentum into the surrounding medium. As the jets pierce the cosmic web, they carve channels that later become conduits for cooler gas, influencing galaxy formation far from their origin. Next, we'll descend to the remnants of stellar explosions that also seed the web with hot plasma.
Radiant shock waves from supernovae inflate bubbles of superheated gas that can reach diameters of dozens of light years. When a massive star ends its life in a cataclysmic explosion, it ejects material at tens of thousands of kilometers per second, heating the surrounding interstellar medium to tens of millions of Kelvin. These remnants, visible as glowing nebulae, enrich the galaxy with heavy elements while driving turbulence that mixes and spreads hot plasma throughout the galactic disk. Over tens of thousands of years, the bubbles merge with neighboring structures, contributing to the larger filamentary network of the interstellar medium. Their collective effect helps maintain the temperature of the galactic halo, setting the stage for the next, more expansive stellar wind bubbles.
Majestic winds from massive O-type and Wolf-Rayet stars carve out enormous cavities in their natal clouds, heating the gas to several million Kelvin. These stellar wind bubbles expand at a few hundred kilometers per second, sweeping up surrounding material into dense shells while the interior remains a searing plasma. Over millions of years, the bubbles can grow to tens of parsecs, creating hot, low-density regions that serve as launch pads for future supernova shocks. Observations show that such bubbles often intersect, forming larger, interconnected hot zones that weave into the galaxy's filamentary structure. Their role as distributors of heat and momentum is essential for sustaining the warm hot interstellar medium, a precursor to the colossal filaments we'll encounter next.
Deep beneath the Perseus cluster lies a network of luminous filaments that glow in X-ray and optical light, tracing streams of plasma at temperatures of several million Kelvin. These structures, stretched over hundreds of thousands of light years, are thought to be drawn out by the cluster's central supermassive black hole, which pumps energy into the surrounding gas via gentle outflows. The filaments act as cooling channels, allowing hot intracluster gas to condense and form stars, while simultaneously remaining embedded in a sea of superheated plasma. Their intricate geometry offers a glimpse of how localized black hole activity can sculpt the broader cosmic web, and they hint at the massive bridges that dominate the universe's largest scales.
Unseen to the naked eye, a massive bridge of scorching plasma connects the Norma cluster to the Great Attractor, forming a conduit of hot gas that spans tens of millions of light years. Detected through subtle distortions in the cosmic microwave background and X-ray emission, this bridge appears to channel matter toward the region that pulls our local group toward the Shapley supercluster. Temperatures within the bridge are estimated to exceed 50 million Kelvin, making it one of the hottest known intercluster filaments. Its existence underscores how gravity can weave together disparate structures into a unified, superheated tapestry, setting the stage for the ultimate giant of our countdown.
Finally, the Hydra Centaurus superfilament stands as the most massive river of superheated gas ever mapped, stretching over 300 million light-years and linking several of the nearest superclusters. This colossal filament, bathed in plasma at temperatures of 100 million Kelvin or more, acts as a gravitational highway funneling galaxies, dark matter, and hot gas into the dense nodes of the cosmic web. Observations from X-ray surveys and Synev-Zeldovich effect measurements reveal that the filament's density, while still low, is sufficient to dominate the local thermodynamic balance, influencing star formation across vast distances. Its sheer scale and temperature make it the ultimate example of how the universe's largest structures are sculpted by streams of blazing plasma, completing our journey through the hidden rivers that shape everything we see.
We've journeyed from modest Seyfert outflows to the titanic Hydra Centaurus superfilament, witnessing how superheated gas streams bind galaxies into the grand cosmic web. These rivers of plasma remind us that the universe is a living tapestry, constantly reshaped by forces far beyond our daily view. If you enjoyed this exploration, subscribe so you don't miss the next mind-blowing list, fresh space wonders every week. Which stream left you in awe? Let me know in the comments below, and if you found this video insightful, give it a like. Thanks for watching, and keep looking up.